Hello everyone, my name is Petar Maymounkov. I apologize for this, but I can't get the Google slide thing to work properly, so we'll make do. And I also cannot see anything here, so. But anyway, I'm going to talk about the Go circuit project. And I also want to thank Richard before me. Actually, he set up the stage for this quite nicely. So I'll get straight to it, and the first order of business would be, is this working? Yes. So to motivate sort of what are the problems that the circuit is solving. And the high-level picture is that the high-level picture is sort of summarized in one sentence, which is that currently in industry there is a big friction between essentially dev and ops. So the dev engineers, the people who make software, and this is all about distributed cloud applications. And then the ops people who have to install them in companies and make sure that they work. There are many specific practical problems that can be mentioned, but I've chosen a couple that are sufficient to sort of motivate the design of the circuit as a whole. So let's look at some specific problems. So the first one that I want to highlight, actually, can you hear me when I'm speaking over here? You can? Speak up a little? Okay. So the first problem that I want to look at is perhaps you've noticed that cloud solutions, meaning very complicated distributed applications that contain multiple components, database, UI services, and so forth, they're never distributed really in any kind of standard fashion, and people typically distribute sort of modular components like a sharded database or a UI service of some sort. But you never get solutions. You get solutions from companies that give them to you as a software as a service. And we want to sort of understand why this is the case. And I also want to convince you that this is actually a huge problem. My favorite example of why it is a problem that we cannot distribute cloud solutions is, let's say, monitoring systems. So most companies that have some scale sooner or later run into this problem where they have to build a monitoring system. A monitoring system is this sort of generic thing that basically continuously monitors all the vitals on all your machines and all the other processes that are running in your data center, and then it ships them over to a time series database, and then usually you have some kind of a non-trivial visualization framework that can show you what's happening so you can debug problems and so forth. Now, a lot of companies are building the exact same thing from scratch internally when they hit the size of scale, when they actually need to have a system like this. And it turns out that this kind of thing actually wastes a huge amount of human, specifically ops engineering effort, because it's not as simple as it seems on the surface to just tie a database to whatever's producing the data and to some kind of a visualization service. And so actually, not only there's a huge cost paid up front, but this cost keeps on going forward. And the fact that this is such a sink for human time has actually created a whole little ecosystem of startup companies now that are trying to, in this particular example, provide monitoring as a software as a service. But this is not an ideal solution in many cases because people usually don't want to ship out low-level technical data, sometimes for security reasons outside. The real technical reason why people, so I want to point out two technical reasons. There might be many more, but these are very important reasons why we're still not able to ship complicated cloud solutions the way we can ship RPM packages for single computer software. The big reasons are that any distributed application needs to know how to start new processes, especially if it's a very complicated application. And they also need to be able to provision or to negotiate the provisioning of new hardware if it's a fancy elastic database, for example. And none of this, you can't really get an elastic database open source, and I'll qualify this statement more carefully. But the crux lies in the fact that a cluster of computers, gives you all the general computation facilities that you get from a single computer, but it also gives you two new semantically different things you can do, which is starting jobs and perhaps asking for more hardware, which you don't have in the single computer world. And as an artifact of history, we just don't have a way of allowing applications to request these things programmatically in a standard way. And the other place where so the fact that we don't have these things as a standard sort of thing also shows up. Like I said, you can't actually truly give me an elastic database because whatever you give me, there's no way you can how are you going to ask me to provision new hardware? I mean, this is what elastic means. And in fact, I think that in general, when you give me some kind of a finished distributed application, really, I should be able to run it and forget about it, except when the application needs to needs something done that it just cannot do on its own, like, for example, getting new hardware. And I'll expand on this idea more. But for now, essentially, I want to focus on the fact that these two things, requesting job execution and negotiating hardware, is something that if I'm the author of open source software like a database, I couldn't possibly write my open source database in a way that is going to run in everybody's data center no matter what the configuration is, because I have no idea how you start processes. Do you just start them as a Linux process, or do you actually have a complicated job scheduling system like Hadoop that you would prefer to use, and so forth? So there's no standard for this thing, and that's the big technical crux why people don't, for the most part, distribute complicated cloud solutions. People do distribute modular components like a sharded database and so forth. And the way they overcome this problem here is they give you a documentation in English, which you have to manually read. So this is the ops team in your company. They have to read this. Then they have to go on to Puppet or whatever else they use for deploying and provisioning software in their data center. And the bottom line is that you basically force them into all this manual work. There's many other technical stumbling blocks, but these are the big ones. So we're trying to propose a solution here, or at least attempt a solution which is not meant to be backwards compatible, and it's a solution that only works for people who are willing to use Go. So this is not a panacea for all problems, but it has some interesting ideas that might be transferable to other places as well. So if I'm going to be proposing a solution, so let me take another, just say a couple more words here. There are ways, of course, to get around these problems. Like, for example, you can build your application such that it has a custom API point where it requests these things, and then the ops people who are actually deploying the software can, hook up to this API. But this is not a solution to the problem that I really care for, which is to reduce the human involvement when it shouldn't be really necessary. Another way people go around this problem is that they say, look, I'm building an application, but you have to use the following framework to run it. And the issue with this is that, there's a bunch of obvious issues, like maybe I don't use the framework that you have built your application for, especially because, and actually most of the frameworks that are available out there that would give you something like this, they solve a whole set of other problems as well, and they're too heavyweight to adopt them just because you want to install my application. So I'm looking for some solution that would be very easy and completely kind of a no-brainer to deploy with your ongoing sort of infrastructure. So, and so basically, the crux of this thing is that we're looking for some standard way of allowing applications to request these things programmatically. This always basically means one thing. We have to have some universal format for expressing the application that I want to ship to whoever wants to use it. And really, true isolation between application development and ops means that if I'm the application developer, I can write the application one time, never touch it again, and this application can now run on any spectrum of sort of different data center setups with minimal involvement of the ops teams. And of course, the other thing is that if I'm going to be proposing something like this, I better make sure that it can be adopted incrementally and without disturbing your current systems. And so this kind of, I mean, we can leave it at this, but basically it has to be able to, like, you know, perfectly fine run alongside with other software that you might have on your machines. And it really should be minimal. And I'll make this very precise as, further on. Down. Okay, this picture here is just to give you an idea of how much exposure a cloud application has to the human, you know, ops engineers in a given company. So, you know, it's a silly picture, but so what I have here is two hosts, two machines that are running your application, whatever it might be. And just to give you, just to show you like just a random list of things that ops people have to do. For start, you know, they have to, of course, configure the application. And the thing is, the application kind of has two kinds of configurations. One configuration has to do with whatever the application actually is doing. This is something that you always have to do. But every application also has infrastructure-specific configuration. If you're starting a MySQL server, you basically have to tell it, you know, which ports to use, and you know, if you're doing a Zookeeper thing, then you have to tell all your Zookeeper instances essentially how to find the other ones and so forth. And unfortunately, every open source product out there basically has a different sort of, if you will, even just the file format of how you configure things. And so it always requires manually reading the documents and setting up the environment so it can run. But this is not the worst. The worst thing is that a lot of applications require straight up manual effort. So, you know, if your MySQL shard dies, you know, restarting it, replicating it, and recovering from this thing is basically a manual process. You know, people have written a lot of scripts that actually automate a lot of, you know, parts of this manual process, but the process remains manual. And this is a cost, a human cost that you pay forward, you know, forever, essentially. And what I want to sort of illustrate with this picture is there's way too much exposure. So the black stuff is your app. There's way too much exposure to the red stuff, which is like human involvement on the ops side. And I want to avoid this. And this is, of course, I'm going to repeat this. This is what has stimulated some chunk of the software as a service industry. And what's really ironic is that really what they're providing is not software. In a lot of cases, what they're providing is essentially the human effort that happens behind the doors of their company. They're not actually, because they're using the same software that you would actually use. And of course, over time, they try to get better, but for the most part, they're not like giving a true technological solution to the problem. So this slide here really summarizes what I think a cloud application, a finished cloud application should look like and behave like. First of all, I should be able to get any new cloud application and deploy it with a single click, just like you can deploy any application on a single computer with a single click. If you think about, let's say, the GNU, the compiler tools and whatnot, this is a horrendously complicated and complex, complex is the correct word, project. And yet you can install it with a single click for the most part, and you can just start using it. You can't say the same thing for distributed applications. I think so. The state of the world in the single sort of computer is that you run the application and then the user just uses it. There's no other, for the most part, interaction. In the distributed world, you can't quite have that because, like I said, there are certain things like physically provisioning hardware that applications cannot do themselves. So the perfect shape and form of a distributed application would be this. You should be able to deploy it with a single click, so to speak. The user, and it's going to have some API where the user does whatever they do with the application. At the back of the application, there should be a very narrow interface, which should be essentially the same interface across any kind of cloud application that you might build using the framework that I'm about to propose, or any framework that ends up being a standard in the future. This interface between the application and the ops team should be very well defined, very simple, and very skinny. So in particular, the kinds of things that vary across different data center setups are sort of like, for the most part, they're just three things. First of all, networking, okay? We don't know ahead of time whether data centers prefer to use TCP or something else to connect between different hosts. And currently, the industry always ships all these services that use TCP. This is presumptuous, but unfortunately, that's the state of affairs that we have at the moment. But you actually have to ask the ops team to tell you how to connect from one machine to the other and what's the namespace of these machines and so forth. The other thing is, like I said, the job execution. You don't know a priori how to start a new process on a remote machine. And the final thing, like I said, is hardware negotiation for elastic services and so forth. So the aim of the project that so the final goal of this framework that I'm about to describe to you is to be able to enable you to write applications once that can then all be run like this in a black box. And most importantly, no matter how many different applications you write, the ops team here only has to learn one time how to provide these functionalities to your applications, and they're all going to work fine. So let's go right ahead. And so I'm going to uncover the solution concept in little pieces because there's a lot of information. So I'm going to start with an overview, right? First of all, the distribution format that I postulate I want to use in this case is I want to distribute cloud applications in the form of a Go source. Now, there are deep semantic reasons why this is a really good choice. But I'm also going to tell you some sort of side practical reasons which actually have little to do with the circuit itself, but it's good to have them in mind. So the Go language is so simple and it's so well instrumented. I mean, the library of the language is so well instrumented with a parser for the language itself and so forth, that if you accept outside code in Go format, it's actually extremely easy to instrument it in all kinds of ways. You can even people who have no experience writing grammars and parsers and whatnot can easily, for example, instrument their code to, they can hook up something like the Google Dapper tracing system to all the function calls that happen in the code. And this is how flexible the language is. Not to mention that it's very easy to, you can look at what packages and libraries an application is using, and you can automatically substitute them with your own, if you cared for this. And so on and so forth. And of course, I think there is a bigger reason why it might sound odd that in some cases that you want to distribute applications as source, but when it comes to debugging, obviously this is quite helpful. So the framework that I'm going to describe to you over the next slides is going to give us the promised isolation between ops and application development. And the final thing is that the applications that you're going to end up building using the circuit are going to essentially amount to compiling your code into a single executable that in fact the ops people are going to compile this, but this happens one time. And this one executable can then be deployed in the most sloppy way, meaning that you just run it on however many hosts you want to run it. And this is, this is what people are already used to doing, because this is the format of most kind of standard, sort of distributed applications that you get nowadays. And just to give you a metaphor of what really is happening, is you are actually compiling all the infrastructure that the cloud application needs into this executable. So as far as the ops people are concerned, they just have to run it without worrying semantics, consistency, just run it on the machines where you want to use it. And then this executable is actually internally going to organize the application in however you want it to behave, with different kinds of services and so forth. But to you, this is all opaque. To you as the ops engineer, this is all opaque. And you're just seeing the same process running on a bunch of different machines. So now I'm going to start slowly digging into more details of what's really happening here. So first I want to talk about this concept, which a lot of you have already heard of. This is the concept of a single system image. This is a vague concept, but effectively what it means is that you want to provide a clean interface to the functionality of some hardware below. And this clean interface is provided to the application engineer so that they can write their code, and then this code can run even under small variations of the underlying hardware. And let me sort of give you some examples just to sort of get your brain thinking on this. So Linux actually, or any operating system, but Linux, for example, is a single system image which gives you an interface between your programs and the hardware of a single computer. And this is not to be taken for granted, and it's like the simplest example of a single system image. And of course, there are many places in the software stack where you can choose to draw this line, the interface between applications and what's happening underneath. So Linux draw this line essentially at the binary level. You can have an executable, and by doing sort of system calls, they get captured by Linux, and all these binaries can count on having the POSIX systems calls being implemented. Then you get into much more sort of like exotic and interesting different kinds of single system image. A lot of people in the past have tried to do something which is really the classical example of a single system image, which is they want to take a cluster of machines, and with a lot of very complex software, they want to make it look like a single Linux machine, so that you can retroactively basically run anything that you have as software written for a single machine. These efforts have kind of failed for the most part, because they're trying to do too much. In particular, they actually also try to conceal from you the fact that some computers die, and this is very hard to do. In fact, basically, no one's really properly done it, and so a lot of these projects are not used at all. But the main thing is that they're trying to do too much. Sometimes you don't want your framework to be too intelligent. Another one, this very interesting example is Plan 9. Probably one or two people here even know what Plan 9 is, but it's worth saying. So Plan 9 is basically, it's an operating system, but really what it says, it's really just a protocol that says if you have a cluster of machines, you can run whatever software you want to run on them, but I want all the software that runs on these machines to expose its functionality in the form of a network file system. And the single system image is drawn here at the network level, meaning that do whatever you want on the computers, make sure you always talk using the same protocol. So really what you see your system, your cluster, as just as a set of file servers. It's an odd example, but it is an example of a single system image. Now, then you have Erlang with its sort of runtime, which is a very interesting case. In this case, you get like a set of, again, a cluster of hardware presented to you all the way at the programming level. So you basically, so the fact that you're running on different hardware is kind of concealed from you, and you get to take advantage of it by being able to spawn many different threads, communicate between them, and these are all sort of baked into the language, so it's quite type safe and easy to do this. And so at the end of this line is basically, the circuit is similar in many ways to Erlang in the sense that it says we want to give you a single system image of a cluster at the language level. And obviously, whenever you're picking a language to present a whole cluster at the language level, of course this language has to have concurrency because this is really the power that a cluster gives you. And the difference between Erlang and Go Circuit, as we're going to see, is that Erlang, the runtime of Erlang is, I'm not a specialist there, so I don't want to like make any hard claims, but for the most part is like a big monolithic thing that you have to install. Whereas the Go Circuit, like I said, and you see, compiles directly into your application, so I can actually give you my application and you don't have to install OTP runtime before you can use it. Nor do you have to learn how to use and maintain the OTP runtime. And so the word minimal here, so minimal single system image, this is a word that I've coined to sit in front of this guy, is specifically emphasizing the fact that it's a single system image interface to some hardware, but very explicitly, I'm not solving any problems whatsoever, meaning any algorithmic problems. I'm not trying to conceal failures of machines or network from you, and so forth. This framework is simply abstracting away exactly the functionality as well as the failure conditions of a cluster to the programmer, and then it's your business to know how to deal with them. But it's quite easier to deal with these things when you have them presented to you in a very clean semantic way. I wanna say why Go was the language of choice, and it's for very different reasons than what Richard was talking before. But actually, I think Richard actually mentioned this as well. So you know, most of you already work in companies that have big data centers, and when you design essentially what's going to be happening in your data center, you know, how does the information flow from one service to another? You know, do you even have feedback loops between services and so forth? You start by thinking, you know, at high level, what are going to be the services? How is the information going to flow, and so forth? So you're thinking in what's called the CSP model. So basically, at the data center level, you have independently independently running processes, which are the processes running on different machines, and they are communicating sequentially, obviously, through the TCP links. So at the data center level, you're already thinking in the CSP model, and so my sort of short pitch here is this. Why switch the concurrency model, you know, when you go from across computers to inside, you know, and there's a big cost if you switch, because you know, typically you design your solution, you know what the information flow does and so forth, but when you sit down to program it, usually in the asynchronous model, because this is the most popular model currently in the industry, I would guess, the cognitive load of sort of rephrasing your data flow, you know, logic into an asynchronous thing has tremendous costs, which I'm not going to talk about them now, but I'm always happy to talk in detail and answer questions. And so we chose the Go language so essentially because it has the CSP model baked in. We could have chosen Erlang, of course, and then the second reason why the Go language is the choice is because industry seems to continuously want an imperative language, especially when it comes down to implementing low-level systems things. And remember, the circuit doesn't solve any sort of special problems, reliability and whatnot, which means that the circuit is very much going to be used by people who are implementing low-level applications like, you know, a locking service like Zookeeper or or chubby, in which case you really want to be able to see when a computer goes down. So, meaningful stack traces is something. So in asynchronous programming, if you don't know, the stack traces are completely useless because if you stop your process, you just see the main event loop and it doesn't tell you what's the state of your application. Whereas in CSP languages, you actually see the threads of the stacks of the different threads, which usually have like very meaningful. They have like a meaningful application. They have an application meaning that you can assign to them and figure out where the bug is. And actually, this is extremely important because in my experience in the past, so there's two kinds of problems that can happen in production, right? One problem is, a process dies and you go there and you look at the stack trace and, okay, so it's useful that we actually have meaningful stack traces. But there's also these other kinds of problems, like what happens if a server in production actually hangs but doesn't die? This thing is nearly impossible to like reproduce and debug unless you could. I mean, these things happen rarely, so the first time it happens, you really want to extract as much information as you can. And if you didn't have the meaningful stack traces, it takes almost a year to find some evasive bugs. So bottom line, CSP is very good for debugging and tracing as well. So this is why we chose the Go language. And so now, abstractly, I want to tell you essentially what the architecture of an application using the circuit looks like. So you have your hosts here with their Linux running on them or whatever other operating system you want. The application that you write, think of it, so it basically uses whatever the circuit is going to give to it in terms of, concurrency primitives and so forth. And your application is written in Go. What the circuit does is it translates this high-level convenient semantic sort of source code that you write into very, very basic networking operations and some spawn operations that sort of correspond to when you want to start a process somewhere. And these are all abstract operations, and there are very few of them. They're very simple in terms of what they're supposed to do. So whenever you give your application to a company, the ops team in this company, all they have to do is they have to write a driver that just simply implements these things, which is elementary to do in most cases. And if you have a very fancy infrastructure, maybe you have to put a little bit of work, but you only have to do this once. And so not only this, but once you start running your application, the only exposure that the ops team has to your application is standardized. Like the ops team doesn't talk to your application itself. The ops team just works with all the instrumentation that comes with the circuit so they can monitor what's happening without understanding what your application does. In fact, if you remember one thing from this, ops engineers should not have to know the first thing about what your application actually does. It's not their job, okay? And the fact that they do is just an inefficient thing, and there's plenty of examples of this in industry. Okay, so this is like the abstract high-level architecture of what a circuit application looks like. And now I want to start giving you a slightly more tangible feeling of what's really going on here. So circuit programs, so these are the applications that you write, they really are nothing else but just a sort of a straight-up Go, it's Go code. It's going to be compiled by the Go compiler. And the only thing is that, so they import the circuit as a package. So they see the circuit really just as a package in the programming language. And this package gives them some new functionality where they can exploit the fact that they're running on a cluster. The circuit itself is this fairly smart package that does all sorts of things. And somewhere in the circuit says, OK, I'm importing drivers for networking and job. But these drivers don't actually exist anywhere in the circuit code. And so when an ops engineer takes your program, they actually have to place drivers wherever they have to place them so that your application can actually work. So this just gives you an idea, literally, in sort of tangible terms, what is a circuit application? And so again, what a circuit, when you actually start running your application, what happens is, so your application here has all sorts of, it's straight up Go code that maybe creates multiple Go routines. They talk amongst each other and so forth. The key thing that the circuit is going to give you is that you can actually start Go routines on other machines. But once you start them, linguistically, they're no different than Go routines. They're in the same process. So metaphorically speaking, you should be able to take any program written in Go, and with minor boilerplate kind of tweaks here and there, you should be able to make it distributed in virtually no time. And so the applications are the application that you write. It's the same source code across all instances, but it's the code is running at different points in the code, and the application really is thinking that it's talking to another Go routine in the same application. But really, what's happening is high-level linguistic communication gets converted into very low-level, very simple networking operations to get physically to the other side. So that's what the circuit is sort of in more concrete terms. And this slide is just to give you sort of a sense of how complex the kind of things that you can do with the circuit are. This is a project that's going to be released in a few months from now. But this project essentially takes your data center and becomes essentially, it can run any legacy Linux process in a Docker container that is instrumented in such a way that all the processes in all the containers, no matter where they are physically, they think that they're part of the same Linux system because you can instrument your Docker container to give them the same view of the system. They can see all the processes in the same procfs, even though they're not actually on the same system and so forth. This is a solution that's kind of makes legacy software be able to take advantage of the circuit, and it's a whole distributed operating system. So the takeaway here is that you have to think about the circuit as an implementation technology for what you really would use as an end sort of user framework in your company. Just like C is just an implementation technology for Linux, and you use C here and there outside of the kernel, but not so much. So that's kind of where it sits in the stack of things. And let me just see how much time we have. Actually, do we know? Does anyone know how much time we have left in terms of minutes? Oh, 0, okay. I can end here. The next few slides were essentially just to give you a taste of what it looks like to program for the circuit. They're like 6 or 7 slides, so I'm just going to swipe through them. But the main thing is, for a start, you take any legacy Go application, if you just include the circuit in it, it already becomes a circuit application. It will take advantage of all the instrumentation that it has in it, even though you're not going to use its other features. And all circuit applications are compiled exactly like you would compile a Go application. So you don't actually have to learn anything new. And so I'm going to skip these slides. The takeaway from these slides is that the circuit really gives you like 2 or 3 functions from this circuit package that you include. So there's not much to learn. Really, to be perfectly honest, really the only thing that you basically have to learn is that the circuit gives you this new function spawn, which runs a function onto a destination that you pick instead of in the current process. And that's the only thing you have to learn, because I have gone through sort of great lengths to make sure that you can basically pass the circuit a function that's implemented in your Go code, and using the reflection package of Go, which, as Richard said, is extremely good, I can do so much reflection that your code can be just native Go code. You don't have to think that, you don't have to worry that you intended it to be run across different machines and so forth. It just works. And anyway, so these are like the specific examples. I told you that the circuit essentially translates between language and networking operations. And anyway, it has instrumentation and so forth. But I think the important thing was that we actually managed to get through the architecture, which shows you what, what it actually looks like. Yeah. Anyway, are there questions? Okay. I mean, you can always, shoot me an email. I'm sure, I'm not hard to find, but I'm, happy to answer questions. Thank you.